So we're moving back to our atom splicing and making a computer based upon an atomic computer, and what its benefits would be in the small term and in the longer term, let's say. So I don't know. Let's do the very crude drawing, shall we? If you're going to be able to see this, we've got a star, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and your dwarf planets, Pluto, and so on and so on. Anyway, so probably not going to get it on this board, but it doesn't matter. So I'm going to make mine egg-shaped on here because it's... But this, let's say this is the heliopause. Actually, it'll be more over this way, to be fair. So the heliopause, at the end of the heliopause, is also known as the Oort cloud. Lots of leftover junk from the creation of our solar system is all there. All dots around us. Okay, and Voyager, the probe, the space probe that was sent up many moons ago, let's be realistic, is somewhere entering that area, yes? The problem is, it takes 20 hours and 33 minutes to receive a signal from there. And you think, oh, that's pretty quick. That's the speed of light. Yes, at the speed of light, you ask Voyager to do something for you, like take a picture and send us that picture back to Earth. So that's not from our sun. That is from Earth. Yes?
Yes.
Yeah, I did do that right, I think. Mercury, Venus, Earth. Right, yes. So that signal is to reach here, and that takes 20 hours and 33 minutes, right? So let's say to send a signal to Voyager, take a picture, and then send me back the picture. That would take you 2 days.
Yeah.
So 2 days for that picture to reach you. And the next thing is, so we understand that signal sort of is a bit like this, right? It's really strong here, sort of gets a little bit weaker here, bit more weaker here, bit more weaker here, and so on. So the chances of us catching this data, another thing is, what quality of a picture are you going to be expecting to get? A nice HD high definition? No, forget it. Because you're only going to be grabbing a small amount of that picture, and it will be an artist's best rendition of that picture, blah, 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 XYZ. Probably not on the Voyager, but most of them it would be more logical to do it this way. So that's working with the speed of light. And let's say our nearest star. So if it takes 88 years, yes, travelling at the speed of light, mind you. If it takes 88 years to reach your nearest star, how long do you think it would take for a picture to be sent back to the Earth? And that's if you could grab it. I mean, it's like trying to catch a cassette tape. Someone, you know, you're blindfolded, you've got to go and stand at the other side of a mountain, and someone's going to shoot a cannon's worth of cassette at you. You've got to catch it. That's the odds of you being able to intercept that, because, you know, there's a lot of noise in space, and you do lose the signals. So, you know, it would probably take around this time, if it was travelling at the speed of light, which it usually is, 88 years for you to see a very, very naff picture. But yet, with an atomic computer, where you splice an atom, send half a spliced atom over here, let's say we could get there.
Yeah.
And based on its rotation, send you a load of series of ones and zeros. We could do it this way. And the computer that's on there, yes, is in control. So if we cut an atom in half, and we cut it dead in half, you get two pieces. One piece stays here on Earth, and the other piece goes in a space probe, and it is then sent out to the nearest star, or whatever. Anywhere in the solar system, take your pick. This gets then sent out. When it's there, the rotation of these, the computer that's on board will take a picture, and it will then code this information into the atom. And the numbers would be that if you rotate an atom there one way, one revolution followed by a reverse revolution, yes?
Yeah.
One spin one way, one spin the other way means 0. 2 spins one way, 1 spin the other way means 1. And so on. 4 spins, 5 spins, 6 spins, D, B, F, G. If it goes in reverse, this is 1, 2, 3, 4, 5, 6. And anyway, so this could do a lot of different ways to get this information. Now, anyway, the computer, if it was to send that, it would take 88 years. But the miraculous thing is that another atom, the one that's at Earth, yes, would begin rotating instantly at the same time as this one was being spun in many opposite directions. In the now moment, it wouldn't take 88 years. It would happen right now as it was rotating. The other one would copy it. That's when you splice an atom. The behavior of atoms is very strange when you cut them in half. One go one way, one goes the other way, and then the other one copies it. And then it would tell this computer back on Earth, it would say, okay, this is a 1, 0, 0, 1, 0, but put in some code, whatever. It will say, picture, build it like this. So the instrument has the capability of building a picture here. Based on those 1s and 0s, goes into this one, it reads it, and then is able to rebuild you the exact same picture back here on Earth right now. Now, in the now moment, you'd see it coming up on the... Just as it was building it, you'd see it. And why would that be so great? Well, if you were there, let's say 88 years, and you discover some life and you need the probe to turn around and go back and have another look. On Earth, if we wanted to tell Voyager to turn around, it would take 20 hours, 33 minutes for it to receive that information, and that is no way near 88 light years away. It's 20, which would be 2, I guess. You could say it like that. I don't know if it is. 20 hours. No, it's not quite. That's per light in that amount of time.
Yeah, that's one way only.
That's one way.
And a half. Half.
Now, if you were 88 years away to your nearest star and you wanted it to do that, doing it the old-fashioned way, it would take you 88 years to get that signal to there, to do that.
And another 88
By that time, you would have sent the probe, and your grandkids would be understanding the information that was coming back after you told it to do some commands. If we sent half an atom splice and kept the other splice on Earth, it would tell you right now as it was happening. And if you wanted to have another look and tell the probe to move, the atom in there starts rotating. We start rotating the one on Earth, and it starts sending numbers into the computer, which then code the computer, which then the computer then on board then tells the rockets, okay, propel, we want to go around this one, blah, blah, blah. And you could watch this live at the time. This could be telling you back on Earth whether it is successful or not, or, you know, either or. And then you'd be able to get more pictures, more data. The more you understand about your environment, the more you conquer it. We don't know much about space. We know more about Earth, but we don't know much about space. And space is supposed to be easier, considering it's emptier. But it's just the distances that make it tricky. Now, every periodically, the Earth has a meteorite that comes in and smashes into the Earth. So let's say Voyager was now detecting that something was moving close to the speed of light, a meteorite, yes, micro and massive. Now let's go for a big one. A chunk about the size of the moon is hurtling towards the inner planets. And Voyager was sensing this with its cameras on board, and it was going to tell the Earth. And it was on a collision course with the Earth from where Voyager's at the heliopause. If that's coming in, and the signal is travelling at the speed of light, but the object is also travelling at the speed of light, you will be getting the signal and the message that meteorite is hitting you soon, right at the same time the meteorite is smacking into the planet.
Yeah, I see.
Now take an atomic computer, and why the push for these next generation computers understanding and different stuff is because you would then, if it was at, let's say, where Voyager is now, it would only take you 20 hours to get that signal, and that might not seem like a lot, but a returned response to it. Now, whether it's made out of hard material, you're going to have to send both. You're going to have to send a warhead into it, that whether it's for a soft meteorite that's hollow, or you're going to have to send another one as a backup to one that is solid. The soft one, if it's going to hit it, it will do nothing apart from alter its course maybe slightly, but it will smile and keep going. If it's more heavy, more dense, then you send a warhead following the lighter one. I would rather be in for a shot of doing something about my fate than nothing at all. That's the difference with this. And also you can have a probe at each and every single one of the planets, sending back this real-time data, not having to wait for you to rendezvous around the front side of Jupiter and you're at the back side of Earth and the signal is now being sent and then the probe goes silent because it now goes behind Jupiter. None of that. That causes delay. And when you don't factor in that an object is in the way, unless you're using an FM signal, that's a straight line signal, more so, less so. AM sort of bounces all over the place.
Yeah.
So, you know, you might be able to get a signal hit and miss on the bounce side. But it's not great. And then you lose data, therefore you lose image, you lose quality, and, you know, your picture then becomes hardly visible, let's say. So yeah, I think, and then when we start to take this, Einstein coined the phrase that you could split an atom. If you rotate one way, the other one will copy it. And given the hydrogen bomb was quite successful, I mean, I'm not going to argue with that theory. Now I want to take that theory and I want to put some steroids into it and make it a bit more. If we take game controllers, the only reason why we see like game pads for the PlayStation or anything, we don't notice this speed of light lag. Everything's traveling at the speed of light, but there is a lag to it. If you could take an atom and put one into the object of your controller and the other one, half of it, into your game's console, the signal will be not working at the speed of light, but at the now ratio. Therefore, that it would increase the speed of a control pad, the sensitivity of it. So as soon as you pushed up, it would move. More quicker, and you would notice the difference when you went back to the old way of doing it, using speed of light. There won't be any loss of signal. Another great thing with these atomic computers is you cannot hack them. There is no way to hack this. So if you were sending an encrypted message to somebody who had the other half of this splice and you had the other half, there is no way to intercept it. You can't grab a signal in any way. It's a spliced item that is spinning one way, spinning the other. Unless you've got the other one be the key, you can't see. No one will be able to hack into this. So what you do remains silent unless the computers that you are using to read the atom were connected to the internet. Then you have a way into that. Via the internet, the connected one, it would be able to read the rotations. There is that. But if it wasn't connected and it was just one to the other, you don't need internet when you've got it like this. No one can eavesdrop on what you do. It's a little crazy and a little hard to understand and a little bit more to fathom in that. But I mean, you would have these dotted around. I mean, lots of these looking over here, one over here. And this is the Oort cloud, one over here, one over here, one over here, and another device over here. And all of those splices would all be on Earth, the other half of the splices, let's say. And if anything moved in these regions, you would know about it immediately. And therefore, there would be more time you've got when it comes to dealing with stuff like this, the more you are able to do something about it, rather than sit like a helpless being on a computer, on a planet rather, and just waiting for Armageddon. This one puts you in the... And you know, if you were going to travel in spaceships and they're going to get up to more to the speed of light and different stuff like that, well, the thing is smacking into something whilst you're traveling like that. If you had this device running in front of your ship, it would be able to tell this one at a now ratio, depending on how far forward it was. You see, if it travelled in a straight line and you've got your half a splice here, yes, and the other half a splice is on your ship, and it's a light year ahead of your ship, and your ship always travels behind it. No matter how way, you always go this way. If this hits into something, this gives you a warning that it's time to alter your course so that you don't smack into anything. And then you need to replace your splice again. This way gives you the closer to the speed of light, or however fast you may go, a warning to be able to do something about that maneuverability. Because you might smack into something, but if you had a group of them at the front of your craft, in an angle so that if you went either way, you always knew that you could always go around it based upon which ones got knocked out because they hit into something, Therefore, they get destroyed, and then the ship's like, right, okay, with a computer reading that, there's things in this way, and this way, but I can go this way because I've still got these splices left. And then they keep going. And then, you know, when you've run out, I guess, you then need to replace them. Depends how wide your ship is, to how big, to how much of those. And then you'll never run into anything. Well, you probably will, your splicers will. But if they're 2 light years ahead, 3 light years ahead, do you get what I mean? The ship is safe. This will hit it, and then it gives you lots of time to maneuver without, you know, causing any too much nastiness. And then you can start to get around the universe a lot more easier, faster. Considering how big it is, it takes a while to get places. You want to be doing everything in the now moment, just like that. So, yeah, I definitely think it's a clever bit of tech. It's different, but it can be incorporated. It's safer. It can have multiple eyes in multiple areas. Then if humans start getting out, you know, and they're working here where Voyager is, and they're mining some stuff from the Oort cloud, because, I mean, you've got a lot of treasure in this Oort cloud. It's getting to it is the problem. Now, let's say you can get to it. Blah-de-blah. Voyager's proved that you already can get to it. The only way to get that treasure, technically, and there's a disaster going down here. Something happened. Now, the people that are going out to mine this stuff are not inventors. They are not... They're just not inventors, okay? They aren't the ones that brainstormed this, and it would be pretty pointless to take a really big instruction manual. You can memorize it, but only to a degree. I think there's only going to be a certain amount that it's going to take in because they're going to be more trained for another purpose. Yeah. It would be far easier to have the technicians and the inventors at Earth on standby if anything happened. But with the old way of speed of light being a problem, 20 hours, 33 minutes for that signal to get there, 2 days for it to then send a signal back of what to do and how to create an action plan. By that time, you've lost your crew. This way, it would do it within now. Then the crew can be answering these questions as they're coming in and firing it back with another splice, telling them what to do, what they need. If you're there and you've completed the mission and got everything and then you've run out of resources, do we just head back? You know, 20 hours and you're already on your way, blah, 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 X, Y, Z. It just gets more... It's more easier, more safer. I guess safety is in the brains, isn't it, of the people that are working to problem solve. So if you get a problem and you're really far away from home, having the many brains at Earth figure and problem solve for you, the ones that are not going through this high-stress situation. If it's all going fuck up on Pluto, let's say, you are going to be dealing with some stress that is quite hard to shut out for a human being, whereas the people at Earth are not in that high-stress situation and therefore can start brainstorming without the need of all of this getting in the way, this emotion, energy and motion, and then can come up with a solution and then give it over as quick as that, and then it will chill the crew out, and then they can... XYZ start coming, you know, figuring it out, works, it's a success. Well, hey, the more successes you have, the more stuff you get back. It's only a matter of time before the star becomes to no longer serve its purpose of giving life. It will then start to take it. And my word, either we want to hightail and have done something about it by then, or I don't know. See you when you get to the other side, you know?
Yeah.
But yeah, so, I don't know. I just think it eliminates this, and I'd rather have 20 hours than it be right on your doorstep with only 5-hour window. 5 hours is still better than none, but 2 days notice might be nice. That depends. Logically, where Voyager is entering is telling you that's how far away it's going to take for you to outrun your star. If it started to rock and roll, because it's going to be a red giant. It's going to puff up. It's going to start losing its outer shell. We're going to get a little dwarf at the end of it. You may be dim, but you're quite hot. Do you know what I mean? That's the type of thing that it will be. And yeah, we don't want to be around for that. So if it starts puffing out and it reaches the heliopause, well, Voyager's telling you in this many years is how long it's going to take for you to get there. That's quite a long time. technologies are getting faster and faster, understandably. But then if you're in a rush, you might smack into something. So, and yeah, I think I'm going to leave this one about here. But yeah, it's just a revolutions, I guess, where you spin your one splice this way and your computer reads it, let's say. So we've got your little screen here, your little coolant bits here, I have no idea, your little keyboard, whatever. And then you got your little atom and it rotate that way once and then go automatically back the other way. Makes A, goes the other way. If it does 2 circles this way, it's a space. So I guess it means space, so you can space a word so it doesn't get all jumbled. Computers don't need that, but humans do. If not, it'll all come out as one text.
Yeah.
Take a bit of time to pick that out, but if you had one as space, so I don't know. You could just start the first one that rotates one way, then rotates back the other way. Whoops. And you could say that then that was space, and then A was one way, and then followed by a reverse. And then B was that way, that way, that way 3 times, followed by that way. Then that gives you B, and then so on and so on. And would you say, oh, that would take a very long time? No, this thing is minute. It's tiny. You need a special type of telescope in order to see it. No, I don't mean telescope, microscope. There we go. See, and then this one would be C, and then it would be reverse this, mirror image this, goes this way that many times, and then one that way, and then that is, you know, you got A for 1, and then this one's 2, and then this one's 3, but in reverse of that pattern. And yeah, then you've got obviously your 1, 2, 3, you got your A, B, C, you got your space for your words, for your sentences, break those up. Can't do full stops, but hey, would you want to? Oh, maybe when you got to the end of your 26, 27 is a full stop. 28 is then, you know, that many rotations that way, and followed by a reverse one. 29 then comes at the exclamation mark. This, that, and the other. Do you see? You can just keep going with it, and because it's so small, it does it so quickly. You'd really have to get a computer. I don't know, a camera, slow-mo cameras, perhaps, to be able to see it. Plus the revolution, you're going to have to make it rotate one way and then rotate it another way. And then high-powered for the computer to understand this movement, be in control of the movement.
Yeah.
And then the other computer have the same input into it, be programmed the same way to read the other splice. So once you cut it in half, one splice goes into this computer on Earth, one goes into there, blah, blah, blah. And then you want another one spliced so that you can have a signal going that way and this way if you need to at the same time. So you can chatter at the same time. So you can also be coding it to do stuff as well as listening to all of the information coming back at the same time. And if you wanted it to do more tasks, then you need 4 atoms, 5 atoms, 6 atoms, 7 atoms on board. These things are so small and minute anyway, they barely weigh anything. So, you know, it's a beautiful thing. Obviously, once you start getting a lot of them, they start to weigh something because you are made up of atom. So when you get enough of them, all at the same time, working together, let's say, they then become heavy because they get dense. But yeah, for computer needs, I don't think you really need that many. A conversation 2-way, maybe 3, maybe 4, open channel. More of these, and then one computer has a lot of splices in it. Multiple computers, multiple screens telling you, I don't know, that then it filters into another computer. I mean, that could be pretty quick. The answer straight there. The picture right there. So, how would a video work? Frame per frame, I guess. Flickbook. Once it's got enough built up into it, it can then start filtering it through. Do you get what I mean? As a flickbook, as an image. Sound? That's interesting. If the computer can hear the sound and know to put this into code, it can tell another computer with that same code how to mimic that sound with the database, you know?
Yeah.
Therefore, if you've recorded enough sounds, you get to understand them. If not, it's a new sound. Catalogue it and maybe see if you can pick it up when there's a crew there at some point to put it into the archive. If it's a very new sound that's not been heard before, it will record it on there. If there are a crew in the future days go by that, they can collect the samples. then put it into the main computer to then, if they hear it in other places, it will then be able to play that sound as to what it's hearing. That's a new one in the database. Okay, save that. Another sound. Okay, that's this. Okay, another one in the database. You might have to collect them in the beginning if they're sounds that you've never heard before. Do you see? Because there might not be anything in the other computer's bank to be able to say, you've got no frequencies in here that will make that. It sort of sounds like this. Based on the numbers filtered in, but you need a program for that. So probably not if it's a new sound. Perhaps. I'm not sure. But movement, definitely if something moved, it could send that. The coordinates could be calculating that as it goes, depending on which one of these it hits into. Could be aiming for Jupiter. And then if you've got one at Jupiter as well, doing its rounds, probably 2, maybe even 4, so that they cover the whole area. And then if that meteorite comes through or whatever, and it enters that one, depending on which one it broke at the time, depending on where they're situated, again, this information can go to Earth. I mean, this is tracking them like real time and all the way throughout the solar system. Are they coming in from somewhere else? It'd be good if they were coming in from somewhere else, deeper space, because then you can send these things further out. So that if they're more further away from your star, and nothing's broke that area, and you can get them to go around quite a bit of your star, the more further back they are and something enters it, the more time you've got. So the longer you have, then you can start refining its trajectory, depending on where it's going to come in, depending on how far back you are. You can then start calculating, predicting. Perhaps you might need to alter your predictions based upon its movement. It might bowl around Jupiter. Jupiter influences it. Jupiter is a hypocrite, really. Sometimes, the Frisbee effect, I think it's called, where a meteorite comes in, and sometimes Jupiter throws the meteorites back out into the solar system, and sometimes it throws them in to the inner rocky planets towards the sun. And yeah, some of the meteorites dance first before they hit into something. And I'm unsure if there's some sort of magnetism within the planets and the star, let's say, that they might start tipping towards it, trying to push a north towards it, if it's more southerly, in a way of trying to deflect it. Perhaps it fails, but maybe it wants some of these meteorites, and then it finds out that it's a southern, and it aims its north at it to attract it into the planet. I think that in the universe, as the way it stands, that everything is always trying to eat stuff. It wants to be big. Planets want to be big, because then they might be able to start fusion. All a planet is a failed star if you think about it. It hasn't gathered up enough in the beginning. Only one got that, let's say. So, you know, it was pulling in at the same time, and there was a race for a star to emerge from out of all of them. So Jupiter as well. I'm guessing this is in a race. There's a race go off, if you get what I mean. So it's technically a failed star. Either way you slice it. So, and they all want to get big in order to start the fusion, and I guess they need to be a certain size. So, I don't know, if Jupiter got a little bigger, do you think it would start its fusion process? Do you think there'll be enough squish on the 3 in the middle of that empty space, enough pushing down? It always looks like there's 3 things trying to occupy this middle space, and it looks like it's darker than the rest of it, like completely right in the center, like really want to push down. And it pushes back. And they can't all occupy the same space. Therefore, they end up creating hot, and the rest of it starts shattering in, because, you know, it backlogs, and the more pressure and pressure and pressure. And I guess this is why there's a small percentage that a black hole is born versus a big one. That there's more push. There's a lot more pushing down, a lot more mass, and therefore it wins. And it can't be in zero existence. If it was to push it, it would go minus 1. That can't exist. That's non-existent, and it doesn't want to do that, so it reverses. It's kind of really weird. It kind of turns it inside out. It's very strange. And it works the opposite way too. Oh my days. This is confusing, but it's also making a lot of sense to me anyway. But yeah. So this one. Yeah. The little fellows. So, I guess you can say atoms are very intelligent. Literally. And I guess without a computer, you might not be able to read it. And the computer, you're able to code the computer, but the computer's able to code the atom and decode it. So you understand the computer understands the atom understands the computer, therefore understands you through this sort of, and also the energy, the electric inside that as well. Oh, isn't this strange? Much like a human, right?
Yes, it
Electricity buzzing in the brain, atoms, computer hardware. Oh, it's nothing quite like doing what's already being done. That is interesting. Serendipity, that. Could you imagine that? There you go. I'm going to leave it there. All done, dude.
is. Okay.